Hello, welcome back to ECE484, Fall 2021. We continue our discussion of discrete time systems today. Probably finish this chapter, early next week. Okay. So last time we were talking about discrete time state space models. So just like continuous time systems, linear time invariant systems can be written in state space form, and it looks superficially at least the same. You have this four-tuple A, B, C, D describing the system. We talked about how you would obtain a state space model from either a difference equation or a transfer function. We did in the case of a strictly proper transfer function, and I encourage you to think about the case of a proper but not strictly proper transfer function. We talked about this conversion from state space to transfer function, and essentially the bottom line is that it looks just like continuous time. And so we have this diagram where you can start with a state space model of a discrete time system. You do the typical computation, the same computation we did in continuous time, and you will obtain a rational proper transfer function. Okay? In going the other direction, so going from a transfer function to a state space model, we basically, based on the earlier results, we will do it by inspection. You can just basically look at the coefficients or the data in the transfer function model and get your state space. Okay? Same thing applies in continuous time, with the caveat that if you start off with a four-tuple A, B, C, D, and you go this way around this loop, back up to here, the four-tuple you get at the end, the A, B, C, D you get at the end, may not equal the original A, B, C, D, because state space models are not unique. Okay, so today we're going to talk about stability of discrete time systems. Okay, we're going to talk about stability in the time domain using state space models, and then we're going to talk about stability in the Z domain using transfer function models. Okay, superficially, these two notions of stability are going to look very different, but they're actually essentially the same notion of stability, just expressed in different ways. So let's start with state space models. And this notion of stability concerns initial conditions. It does not concern inputs. So we're going to look at a discrete time system, state space model, with no inputs. Okay, so you have some initial condition. So, and it's a discrete time system, but your intuition would be like your heart rate. It's something which is intuitively stable. And the idea would be you go and play a game of basketball, your heart rate goes up. That's sort of the input. And then when you stop playing basketball and you stop, the forcing function goes away, you have a new initial condition for your heart. If it's stable, if you're in relatively good health, your heart will go back to its resting heart rate. So it's sort of like stability with respect to initial conditions. Okay? Or if you have you've designed a quadrotor to stay in one particular location, a gust of wind might come and move it away for a second, but when that wind goes away, does it come back to where it should be? Okay, and this is the notion of stability of state space models. Definition. 6.6.1. So we're going to say that that system is asymptotically stable. Is asymptotically stable if for every initial condition we get that x of k goes to 0 as k goes to infinity. Okay? So no matter how you initialize this state space model, no matter what initial condition you pick, eventually the system comes to rest at the origin, right? It goes to 0 and then it stays there. 0 is an equilibrium point, as you can see, for this system. Okay, so how do we test for asymptotic stability? So consider the evolution of the state. starting from x0. So what do we have? We have that x1 is equal to ax0, of course. x2 is equal to ax1, which equals a squared x naught. Right? Continuing this way, it's clear that xk equals the kth power of a times the initial condition. All right? And so this matrix we're going to call the state transition matrix. Okay? And it sort of tells you how the state evolves as time advances due to initial conditions. So as an example, so what is that? That's a rotation matrix. It rotates by 90 degrees. Okay, it's a rotation by counterclockwise rotation by 90 degrees. Okay, and if we were to look at the state, if we pick an initial condition and we run it through that system, what does it do? Well, say this was our x0. Well, x1 will be here, x2 will be here, x3 will be here, and so on, etc. Okay, so the state transition matrix sort of is telling you how the state is transitioning as time advances. Okay. So given all that, asymptotic stability says that we want the state to go to 0 no matter how we pick the initial condition. And so it's clear that that is equivalent to the state transition matrix approaching the 0 matrix. So asymptotic stability is equivalent to a to the k approaching 0 as k approaches infinity. Okay? So one way we could test for stability would be to first compute the state transition matrix and then check if it goes to 0. So let's talk a little bit about that approach. So there are two ways to compute a to the k. One, of course, not surprisingly, is Z transforms. Secondly, we could also use algebraic methods. And to bring up a term which you would have seen before, but maybe not in a while, Jordan form of a matrix is relevant for method 2. So let's do an example to illustrate that. Not from the notes. Okay, so in this example, we have the following system. Okay, we want to know, is this system asymptotically stable? Does the state go to 0 for any initial condition? Okay. Is this system asymptotically stable? Okay, so what we're going to do in this example, we're going to compute the state transition matrix using these two methods, and then we'll determine whether or not it's stable. So method 1. Z transforms. Okay, so what I will do is I will take the Z transform of the difference equation, the state equation that I have above. Okay, so we have that say we have it, that's our system, right? So taking Z transforms, kind of like what we did last class, except now we're not going to assume the initial conditions are 0 because we're not looking for a transfer function, we're looking for the effective initial conditions. So we will get the following using our Z transform tables equals AX of Z. Rearrange to isolate for X. And you will get the following. This guy here. Okay? And so what we see here from this expression is that, going back to the time domain, so we see that the state transition matrix A to the K and Z to the Zi minus A inverse are Z transform pairs. In other words, if we wanted to check for asymptotic stability, what we could do is we can compute that X of Z, that expression that I have there, and then go back to the time domain, and then we'll have A to the power of K. Okay? So in this example, what does this quantity look like for this particular A? So it's Z times Zi minus A. I've sort of covered it a bit, but let's put it in here. Inverse. All right. So there's our expression. We need to invert that matrix. I'm not going to go through the details. We've done enough times, but if you do it, you get the following. Okay. So now we have this expression. I need to take the inverse Z transform of each entry of the matrix, and I will have my state transition matrix. So take inverse Z transform of each entry. To get, okay, so we have to do, we talked about how to do this a couple of classes ago, but you do it for each entry, and you will get the following. So let me just write it down. Okay, so we get this matrix. So looking at this thing, what happens as K advances? Well, you can see that it's definitely not going to go to 0, right? We have this negative 2 to the power of K showing up all over the place. And that's going to, it'll oscillate between positive and negative, but it's going to get bigger as time advances. Similarly, that negative 1 to the K term, it's going to oscillate between positive and negative, but it's always going to be a 1, a magnitude 1. So this matrix is definitely not going to 0, not asymptotically stable. So A to the K does not go to 0 as K goes to infinity, not asymptotically stable. Okay, so that's one way to compute this state transition matrix using Z transforms. Another way is the algebraic, so method 2. Algebraic. And so I said Jordan form earlier. In this case, what we're going to do is we're going to find a similarity transform, or a coordinate change, if you will, that will diagonalize this A matrix that we're given with. So let's remind ourselves how we diagonalize a matrix. Step 1, find the eigenvalues of A. Right? And those are the roots of this. So these are the roots of the following polynomial. Right? We've seen that polynomial before. It comes up when we do our state space to transfer function calculation. So in this case, it's this guy. So z plus 1, z plus 2. So in this case, the eigenvalues are okay, and I'm going to use this symbol for the eigenvalues of A, or spectrum of A. Okay, and so in this case, lambda 1, lambda 2, and they are equal to negative 1, negative 2. Okay, so we find the eigenvalues. Step 2, find the eigenvectors. Find corresponding eigenvectors. V1, V2, right? So the eigenvectors corresponding to the eigenvalues lambda 1 and lambda 2. So these are non-zero vectors. Such that A Vi equals lambda I Vi. Okay, and so in this case, solving A minus lambda I Vi equals 0 gives V1 equal to negative 1, 2, V2 equal to negative 1, 1. Okay, so those eigenvalues I'm going to use to diagonalize my A matrix. So step 3. Jordan form of A. All right, so I'm going to set V equal to V1, V2. And that equation above then, AVI equals lambda I VI. So the equation up here, I can write it in matrix notation, right? It's just that's just the definition of an eigenvector. I can write it in matrix notation. And what does it look like? We have that A times V equals a diagonal matrix, sorry, equals V times the diagonal matrix lambda 1, 0, lambda 2. And this is going to be our Jordan form. Okay, so now we have our Jordan form. It's V is what we really wanted here, and we now have it. And so now we can compute the state transition matrix. Use AJF to compute A to the K. All right, so let's see how that works. We have A to the power of K equals, so look at the equation above. We have that AV equals V times the Jordan form of A. I multiply on both sides by the inverse of V. I can say that this is equivalent to V, a Jordan form, V inverse to the power of K. So I'm using this equation, right? Just rearrange it, isolate for A. V is invertible as long as those eigenvectors are linearly independent, and they are in this case. Continue. What does this mean? This is the following calculation, right? So k times. Okay, so let's make an observation. Everywhere there's a V inverse paired up with it. So these guys turn into the identity matrix. That's going to happen all the way down the line. So basically all the V's and V inverse sandwiched in between go away. And so what we're left with is just all the AJFs in between get multiplied together, k times. And the nice thing about the Jordan form of matrix is it's easy to compute its kth power. In particular, in this case, it's a diagonal matrix. So the kth power of a diagonal matrix is just the diagonal entries to the power of k. So in this case, we get this thing, okay? And now the rest is just algebra, right? Matrix multiplication. Multiply V times this matrix, and then multiply it times V inverse. So let me be in gory detail. V, of course, was V1 and V2, so it's V1, V2. Times this Jordan form to the power of k, and then this inverse. Right? And at that point, it's algebra, and my claim is you get the same answer as before. Okay. So again, what we will conclude again is that system is not asymptotically stable. Okay, fine. So asymptotic stability asks that no matter how you initialize this system when the input is 0, things go to rest. There are no, things go to 0. We argued that that's equivalent to the state transition matrix going to 0. And then we explained 2 ways that you can compute the state transition matrix. Now it's clear that either method is going to be labor intensive, right? It's going to be difficult to do for large problems. And so it would be nice to have a test which doesn't rely on computing the state transition matrix. Okay? And that's what we're going to talk about next. Can we have a test for asymptotic stability which doesn't rely on actually computing this transition matrix? That's annoying, right? We don't want to have to do that if possible. And indeed, there is. So a to the k approaches 0 as k goes to infinity, if and only if every eigenvalue of A has magnitude less than 1. Okay, so we have asymptotic stability if when you compute the eigenvalues of A, they are all magnitude less than 1. Let's do a sketch of a proof. When A is diagonalizable. Okay, we'll prove it in the case when A is diagonalizable. The proof in the general case is very similar, just a bit more complicated and doesn't really, illuminate much more. So let's do the simple case where it's diagonalizable. So if A is diagonalizable, which means, the condition is that it has linearly independent eigenvectors, equivalent, or which is implied by having distinct eigenvalues. Let's say it's diagonalizable by some v, i.e., just like above. Right? So exactly what we did above, where the lambda i's are the eigenvalues. Of A. Okay, so we're going to do the special case where it's diagonalizable. And let's see that this condition of the proposition comes out from this discussion. So what do we have? So we have that a to the k approaches 0 if and only if, rearranging, v ajf to the k. V inverse goes to 0, using the same argument that we used in the example above. Now V is just a constant matrix, so the only and it's an invertible constant matrix. So the only way that that expression can goes to 0. The only way that expression can go to 0 is if the Jordan form of A goes to 0. But it's a diagonal matrix, so what we need is that each of these lambda i's go to 0. Those are the diagonal entries along this Jordan form. And the only way that number is going to go to 0 is if the magnitude of lambda is less than 1. Which is what we wanted to show. Okay. The argument would be very similar in the case when the Jordan form of A is more complicated, not a diagonal matrix, but the idea is the same. Eigenvalues less than 1 in terms of magnitude. Okay, let's do an example. So this is nice, right? So the upside of all this is that for asymptotic stability, I don't actually have to compute the state transition matrix. I can just compute the eigenvalues. So example. Let's look at different A's. So the one we already looked at from the previous example was this guy. And we saw by computing its state transition matrix, explicitly computing A to the power of k, that it was not asymptotically stable. But now with this proposition, I can just check the eigenvalues. So in this case, the eigenvalues of A were -1 and -2. And so with just that, I can conclude that, in fact, I only need one eigenvalue to have magnitude greater than or equal to 1, but in this case, both do. But in either case, it's unstable. What about that rotation matrix that we talked about before? Remember that it rotated the state around the 90 degrees each time. Well, its eigenvalues are j and -j. Both have magnitude 1, unstable. Right? And we know that physically it makes sense, right? The state does not go to 0 as time advances, it just keeps rotating around the origin. What about the identity matrix? what does this thing do? It doesn't move, right? Whatever initial condition you pick, the state stays at that initial condition. So it's not stable, not asymptotically stable, and its eigenvalues are 1, 1. So unstable, and just as an aside, we have that x of k equals x of 0 for k greater than or equal to 0. Right? So it's not going to 0 for every initial condition. What about this matrix? It also has eigenvalues, which are 1, 1, so unstable. Though the dynamic behavior of this system, or this model, is a little bit different, right? In this case, what you'll get is that if you look at the matrix, x2 doesn't change. So whatever initial value you pick for x2, it stays constant. x1, on the other hand, is going to be whatever initial value you have for x1 plus k times the initial value of x2. Right? All of these unstable because they all have at least one eigenvalue with magnitude greater than or equal to 1. Okay. So our first notion of stability is a notion of stability for state space models. Namely that no matter what initial condition you pick, when the input is off, the system goes to rest at 0. We now take a look at this other type of stability, which at first glance seems very different because it's sort of opposite. It's going to involve inputs, not initial conditions. But then we're going to see that these two are essentially the same thing. So next. Bibo stability. And this is applying continuous time as well. So continuous time, it's a similar idea. The conditions are different. In continuous time, the conditions would be on the eigenvalues having negative real part, right? So in continuous time, the notion of asymptotic stability is the same for linear systems, but the condition would be not that the eigenvalues have magnitude less than 1, but rather that they have negative real part. But it would be very similar, certainly analogous. Okay, Bibo stability. Bibo stability is, of course, an input-output notion. We talked about it in chapter 2, all those definitions about what it means to be bounded, what it means to be bounded input, bounded output stability, all those stay the same. Like the definitions of Bibo stability and what boundedness involve are the same. And so now I'm going to just state the theorem for Bibo stability, which is analogous to what we saw in chapter 2 for continuous time systems. Okay, so this is going to look, if you go back and look at your chapter 2 notes, you're going to see this is very much a mirror image. So assume G is rational, proper. Rational and proper. The following are equivalent. So first, G is Bibo stable. Okay. Meaning every bounded input produces a bounded output in discrete time. The impulse response remember that is the Z inverse of the transfer function, G, is absolutely summable. right? So that means that the sum from k equals 0 to infinity of the absolute value of the impulse response is finite. Okay, and you take that impulse response and you add up the absolute value for every time, you get a finite number. Or another equivalent one is that every pole of G has magnitude less than 1. Okay? So very much analogous to what we saw for continuous time systems. First comment. Second comment, it looks very different than what we just talked about. Here, when you talk about transfer functions, you're looking at the forced response. Initial conditions are always 0, so this is involving only inputs. Right? The previous one only involved initial conditions. This only involves inputs. We'll see that they're essentially the same thing. But let's do some examples. So let's do our 5-point moving average. Okay. If you've done the problem set posted last week, then you've already found the transfer function for this guy. But let's do it in your case. So this guy's transfer function, g of z, is given by 1/5 z to the power of 4 plus z cubed, z squared. Oops. Okay. Look at its eigenvalues, or its poles, right? The poles are all at z equal to 0. All poles inside unit disk implies Beeble stable. Right? And it makes good intuitive sense, right? If I'm taking the average of a bounded signal, how could my average become unbounded? Of course, couldn't. And that's checking the poles. We could also check the impulse response. Let me write it down and then we'll talk about it. So what is the impulse response? When you take the input to be the discrete time impulse. The discrete time impulse is 1 for k equal to 0 and 0 otherwise. So you're taking the average of this signal. So for the first 5 time steps, you're taking the average of 1 and 0 for everything else. That's why you're getting this 0.2 average. And then after that, the system loses memory. It has no more memory. The point here is that the impulse response is finite. It's called a finite impulse response system. It only has a finitely many non-zero terms, in this case 5. And so of course, when I sum those finite number of terms, I will always get a finite number. So since G has only finitely many non-zero terms, and again, this is called a finite impulse response system. Of course, when I take the absolute value of those terms and I add them up, I'm going to get a finite number, and it'll be absolutely summable. It's clearly, absolutely summable. And therefore, Beeble stable. Okay, so either checking the poles or checking the impulse response, of course we're going to get a consistent answer, and that's what we've done. Okay, let's do another example. A summer, okay, sort of also called an accumulator. So what's the system model? It just adds up the input. Whatever input you give it, it starts adding it. So it's the previous, assuming the initial conditions are 0, at time step 0 you'll get y is equal to u. At time step 2, you will get that y is equal to the first value of u plus the second value of u. Right? It's accumulating. It's summing up the value of the input. Let's draw a little picture. Using z-1 for a time delay. So that's all it's doing. It's just adding up the previous value, all the inputs. Now, if you think about discrete time summer, this is very much like integration, right? That's what integration is doing in the limit. It's adding up all these values of the input. Okay? And so indeed, this summer is the discrete time analog, of course, of the integrator. Okay, we know that the integrator is not Bibo stable because if you feed it a step, it produces a ramp. Let's see if that happens here. So this is the discrete time counterpart to an integrator. Right, just adds up the input. And if you look at its transfer function, you see that it has a pole at z equal to 1. So all I've done is the stuff we were doing before. Take the z transforms of the difference equation, get a transfer function. Okay, pole at 1. If you prefer, you could find its impulse response. Right, so if my input is just 1 at k equal to 0 and then 0 thereafter, and I add up the input, of course it's just going to be equal to 1 starting from k equal to 0, and then it doesn't change. Now, pole at z equal to 1, bad pole. If I take the absolute value of this guy and sum it up, it is not absolutely summable. So, G has a pole at z equal to 1. G of k is not absolutely summable. So clearly unstable. And if we want to draw a little picture, of the step response for this system. So let's call that k, 0, 1, 2, 3, 4. So let's apply a step input. Well, what is the output? It's the sum of the inputs, right? So the output is going to be so 0, 1, 2, 3, 4. Okay, so 3 ways to check that it's unstable. Checking the poles, bad pole, unstable. Checking the impulse response, can't be summed absolutely, unstable. Third, we found a bounded input, the step, which produces an unbounded output, the ramp. By any of these methods, the summer is unstable, not Bibo stable. Okay, so we've talked about asymptotic stability and Bibo stability. What is the relationship between these two things? Let's check it out. They look superficially very different. One involves initial conditions, no inputs. The other one involves inputs, no initial conditions. So 6.6.3, asymptotic stability. And Bibo stability. All right. Asymptotic stability concern the time domain. So over here we'll have our state space model. Okay. And we know, we saw earlier, that it's asymptotically stable if and only if every eigenvalue has magnitude less than 1. So asymptotically stable if and only if every eigenvalue of A has magnitude less than 1. All right, let's review what we did earlier. Okay. Take Z transforms of that state space model to get a transfer function, right? This is what we did last class. And we know what that transfer function looked like. It's y of z okay. Fine. Let's bring in the formula that we typically use to compute the inverse of a matrix. It's adjoint over determinant. So let's write that. So I can write this as C times the adjoint of Zi minus A, remember that's an n by n matrix, over the determinant of Zi minus A, B plus D. Okay, and that system is Bibo stable if and only if all of its poles have magnitude less than 1. Okay, but now look at the poles of this transfer function. They are coming from this determinant, right? The roots of that polynomial in that determinant, the poles are going to be from there. But those are exactly the eigenvalues of A. The eigenvalues of A are the values of this that make this determinant vanish. And so if you compare these two the conditions, what we see right away is that the poles of the transfer function are a subset of the eigenvalues of A. So let's write this down, that the eigenvalues of A which are the roots of the determinant of Zi minus A, contain the poles of the transfer function. Right? Again, look at the expression for the transfer function. There's this determinant showing up in the denominator. So what does that mean for stability? If A is asymptotically stable, then it has all its eigenvalues having magnitude less than 1, which means that the poles, because they're a subset, must also have magnitude less than 1. In other words, we can conclude that asymptotic stability implies Bibo stability. All right. We'll stop there. It's a good place to stop. But I'll just mention, usually the two notions are equivalent, right? Usually the poles of the transfer function actually equal the eigenvalues of the state space model, of the A matrix in the state space models. but not always, right? So most of the time. We'll do some examples next class to see that when that's not the case. But essentially, the long story short here is that we have these two different notions of stability. One is regarding initial conditions. One was regarding inputs. They look very different superficially, but in most cases they are equivalent. Okay, I will stop there, and I will see you next week. Good luck on the lab, which I believe is due early next week. Okay. That's right. So you could have cancellations. That's right. Bibo stability does not imply asymptotic stability. That is correct. And we'll see an example of that next class. But yeah, that's right. Again, for most cases, they're equivalent. So you'll usually will find in practice that the two notions are equivalent, but in theory or in principle, they're not. Asymptotic stability is stronger than Bibo stability. Yes, that's right. You're absolutely right. In the general case, that's right.